Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosin, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer box. After the presentation, we will begin the question and answer session, and I will ask our speaker your questions from the question and answer box. Your questions in the box will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Mark Snyder from Bio-Rad Laboratories.
Well, first, I'd like to thank all of you for attending this webinar. I hope you find it interesting. Today, I'm going to be talking about packing resins at process scale, focusing on the differences between compressible and non-compressible resins. So as an overview, I'm going to be talking again about the differences between these two resin types, and then go into some slurry preparation techniques, slurry transfer methodologies, column packing guidelines, and then once the column is packed, we need to talk about how to evaluate the column to make sure that it's suitable for use in your process. Finally, I'm going to spend a minute talking about HETP and asymmetry ranges. So, incompressible resins, we'll start with first. The amount of resin that you need to put into a column is determined by the tap settle density. That is, the number of mils that a gram of resin will occupy. Bed consolidation equals bed packing, meaning that as soon as the particles are all down at the bottom of the bed, you're essentially done. These resins settle rapidly, so you have to work fairly quickly. They require a headspace once they're packed because since they're incompressible and therefore fragile, you don't want to drive the top flow adapter down into the bed. And again, best results are achieved with rapid packing. Compressible resins in some ways are the opposite. The amount of resin you need is determined not only by the bed volume, but also by the compression factor that you have to apply. And therefore, you will need to apply additional compression once the particles are all down at the bottom of the bed. Most compressible resins do not settle rapidly, so you do have a bit more time to work. Obviously, there's no headspace once the column is packed because you are driving that top adapter down into the settled bed. And again, rapid packing is not a significant factor. So this is the workflow for packing. You make the slurry, transfer the slurry into the column unless you're making it up in the column, pack, and then qualify.
So in terms of slurry preparation, for incompressible resins, many of them come as a dry powder, which then requires dispensing the correct amount of powder into a slurry tank or possibly into the column, followed by rehydration. And mixing this kind of a slurry requires a low shear impeller. Compressible resins, on the other hand, typically come as a slurry, 50 to 80% in the jug most of the time. The amount of slurry that you will need equals the bed volume plus the compression factor that you'll have to apply. And low shear impellers are not required. Again, a tip about CHT media. Slurry preparation instructions can be found in our CHT application guide at biorad.com/CHT guide. You can also contact our specialist about packing at biorad.com/chromescientist. Now, one last word about low shear impellers. This is an example of what a low shear impeller looks like. This happens to be the Lightman A310 variety. However, there are a number of low shear impeller styles. Any one of them would be suitable. You just need to make sure from the manufacturer that in fact you are dealing with a low shear impeller. So when you're ready to transfer the slurry into the column, you want to make sure that the column is level. Second, if you are using syringe transfer to actually pull the resin into the column by lowering the top flow adapter to the bottom, sealing it up, and then actually raising the top flow adapter like a syringe, you just want to make sure to avoid introducing air bubbles at the end of the slurry transfer, which most likely would necessitate then repacking. Pump styles matter if you're using pumps to transfer the slurry. Incompressible resins require a diaphragm pump. Do not use peristaltic or rotary lobe pumps due to damage to the resin and or the pumps. Compressible resins certainly can use these pump styles, however. Now just a word about CHT. If you're using 40 micron CHT media, you want to make sure that the frit should be 10 microns or less. You can also view packing tutorials on CHT slurry transfer methods at biorad.com/CHT packing. So when you get ready to pack the column, it's important to avoid stratification of particle sizes. What I mean by this is that if you're not packing the column properly, the larger particles will move to the bottom of the column, while the smaller particles will tend to stay on the top of the packed bed. This will lead to poorer HETP results than you could get otherwise. And the way to avoid this is simply using appropriate flow rates and/or piston movement. You want to move at a rate that's faster than the fastest settling particle. Now for incompressible resins, in terms of the bed itself, you don't really need to know the precise height of the packed bed because there's not a compression factor, so there's no need to really measure it exactly to figure out exactly how much to compress afterwards. Packed beds should have a headspace because, again, these particles are fragile and you don't want to crush them by moving the top flow adapter into the bed itself. And if you want to think about compression factors, the compression factor for incompressible resins is exactly 1, meaning there is no compression. Because you're leaving a small headspace, you want to avoid upflow during bed conditioning because this will move the whole bed up and down, which is generally not a good thing. Now, compressible resins in many senses are the opposite. Optimal packing does require a precise measurement of the settled or consolidated bed height so that you know exactly how many centimeters you have to compress the bed to get to your desired compression factor. As a result, packed beds must not have a headspace, and they won't because you're pushing the top piston down into the bed itself. Now, compression factors typically are 1.1 to 1.3, but I've seen them as high as 1.5. And finally, compressible packed beds are typically conditioned with a combination of both upflow and downflow. So just a few notes on best practices for packing CHT. Again, you want to consolidate the bed faster than the fastest settling particle for best results, as I indicated on the previous slide. How fast is this? Well, for 40 micron CHT material, the particles settle at a rate between 35 and 125 centimeters an hour. So you want to go at least 150 centimeters an hour for best results. You can go faster, but you really don't gain anything in terms of bed quality. And for 80 micron particles, you want to go at least, let's say, 300 centimeters an hour. And a packed bed is achieved once all of the particles have found their way to the bottom of the column. Again, you want to leave a slight headspace so that you don't crush the top of the bed. We recommend a headspace of 1 to 5 millimeters between the head plate and the settled bed. Here's an example of a 1 millimeter headspace. And here's an example of about a 4 millimeter headspace.
So now that you've got the column packed, you need to evaluate it to make sure that it's suitable for use in your process. So we're going to talk now about things which are common to compressible and incompressible resins. The test solute must not interact with the matrix. Typical injection volumes are 1 to 2% of the total bed volume. Very importantly, extra column volumes in the test hardware will significantly impact results. It's very important to minimize the extra column volumes to get the best HETP and asymmetry results that you can. Typical test solute measurements are either done by using conductivity or by absorbance. For conductivity, most people use sodium chloride, but a number of cases I've seen people using sodium hydroxide as well as a few other solutes. Absorbance, a lot of people use acetone. Sometimes places don't like to use acetone because of explosion concerns. And in those cases, I've seen caffeine, vitamin B12, and probably a number of others compounds as well. Again, a tip for CHT media, a special note when using sodium chloride as a test solute. You always want to use the same level of phosphate in the equilibration and injection buffer. And in addition, this system will produce an artifactual second peak. And I'm showing you what that looks like here on this chromatogram. The red arrow points to this small peak. It follows the main sodium chloride peak. It is actually a phosphate peak. If you want more information, please give us a call and we can tell you about why this is. It almost all of the time is there. It should be there. It's a normal part using this system, so don't worry about it, and certainly do not include this in your calculations for asymmetry and HETP. Now, a word about HETP and asymmetry, and again, this goes for both compressible and incompressible resins. First of all, the ranges that you select should be based on process development experience. HETP is irrelevant during a step elution. You need exactly one plate. The protein goes on and it comes off. So the acceptance criteria should be based on required performance of your particular step. We provide vendor data that show what we get in our hands. This is what's achievable, and it may exceed your requirements. So I want to give a couple of post-packing tips for incompressible resins. CHT and other incompressible beds can continue to consolidate slightly after initial packing. Think about a box of cereal. If you have a box of Corn Flakes or Rice Krispies and you shake it up, you will see that the volume that those flakes or Krispies occupy is quite possibly less than it was a minute ago. This phenomenon is also observed with silica, with controlled pore glass, with zirconium, with a whole variety of other incompressible media. Additional bed settling can occur during column transport from one room to another. You can also get continued settling over the first few cycles as the start and stop motion of the buffer or the solutions through the resin bed actually provide some additional vibration. If further bed consolidation occurs beyond the original recommended headspace, lower the flow adapter to the original headspace if you desire. But if you do this, I strongly suggest you incorporate these steps into a packing procedure to avoid discrepancies. That's going to make the people on the manufacturing floor as well as the people in QA much happier. So I want to spend just a couple of minutes now going over some packing studies that we've done at Bio-Rad on CHT. So we did a total of 20 independent column packing studies. In these 28 cycles, the parameters that were not being tested in that cycle were kept constant wherever possible. I'm not going to read through the list of parameters that were tested. I'll just go through them somewhat slowly so you can get a feel for what we looked at. I'll be presenting the data on these in just a moment. So these are the data points achieved from the 28 cycles. They span a range of asymmetries from about 0.9 to 2.3 and plates per meter from about 2,000 to about 12,000. Now we have arbitrarily grouped these into three groups, which I'll show you in just a minute: red, green, and yellow. The green box represents points which most people would consider generally quite good following a packing.
This region has an asymmetry between about 0.9 and 1.5 and about 6,000 to 12,000 plates per meter. Again, you should look at your own process development studies and from them draw the data that will show to you what your minimum HETP value is and also what asymmetry range you will find acceptable in your own process.
The yellow box represents studies which were probably reasonable, but maybe let's call it less than ideal. The top two dots represent overnight settling of the resin, meaning that the slurry was simply dumped into the column, we went home for the night, came in the next day, lowered the top flow adapter, and measured the HETP and asymmetry. Again, this slower settling allows bead stratification to occur, and this is reflected in a higher asymmetry value, although the plate count was still pretty good. The bottom 3 points represent 10 millimeter headspace between the top of the bed and the bottom of the top flow adapter. Remember, I said that we typically leave 1 to 5 millimeters. So you can see that increasing that to 10 lowers the asymmetry and plate count. And again, these values were an asymmetry of greater than 1.5, maybe 1.5 to 1.8, and plate per meter values that are between, let's say, 4,000 and 6,000. Now, these last 2 points represent the poorest packing that we were able to achieve. These were done by leaving a 20 millimeter headspace, in other words, 2 centimeters, which again, we don't recommend. And in this case, the asymmetries were 1.8 to 2.3, and the plates per meter were about 2,000. Once again, let me stress that these values might be perfectly acceptable for your purposes.
So I want to thank you very much for listening to this talk. Before I take questions, I just want to make a couple of final points. First is that we offer method development to assist you. We have a network of experts that go worldwide and can be on site to actually help you in the lab do experiments and look at data. I typically do about 100,000 miles a year, although obviously with the pandemic, my travel has been significantly curtailed. We have a dedicated technical support group that can help you on the phone or by email or again in person in case you have any questions or issues during process development. And beyond process development, we offer continued support throughout the lifetime of your product. We can help you with process transfer as well as regulatory procedures. We have dedicated regulatory support files for each one of our products. Before I go on to the last couple of bullets, I just want to say if you ever have any questions about our products, please contact us. This is a large part of my job. It's the part I love doing best. And if you don't call us, we can't help. It's really as simple as that. We have a lot of online resources at biorad.com/library. I want to show, before I get to some of these points, a picture of what some of our products look like. The green capped columns are pre-packed 1 and 5 mil columns that you can order from Bio-Rad and get from your process specialist. We have 96 well pre-packed plates on the far right, and immediately to the left of those you see our pre-packed 200 and 600 microliter columns, which are suitable for 96 well format. We've also shown you some of the pack sizes for our resins. These are some of the smaller ones. Now, at biorad.com/library, you can request resin samples. You can speak to our scientists, including me. You can view packing tutorials, and you can request a customized seminar, either virtual or, once the pandemic eases, on site. So, and one final thing, you can always email us at process@biorad.com. So with that, I'd like to thank you very much for your attention once again, and I'll take any questions.
Hey, great. Thanks, Mark.
Sure.
So the first question is, what are strategies for packing columns through different column sizes for the successful scale-up? For example, 50 milliliters to large process size like 20 liters.
So, in some senses, there are no differences because you're still putting particles, compressible or incompressible, into a round tube that's capped at both ends. However, there are some tactical differences, I guess you would say. The larger you get, sometimes it takes longer to assemble the hardware and it's more complicated, so you want to make sure that the staff is thoroughly trained in how to use the column, how to take it apart and put it back together if need be. One thing that's true is that the larger you get, the less wall effects there are, so you can often run columns at a much higher flow rate in small columns than you can at a large column, so you definitely want to keep that in mind. And I think the third thing is, especially for larger columns, you want to have spare parts on hand because if something breaks, you don't have any time to send to the manufacturer for a spare part and get it back in the mail or whatever. So I think those are probably the differences. I mean, I pack columns up to 1.8 meters in diameter, and really the principles are pretty much always the same. It's just the amount of fiddling you have to do with the equipment that is probably the biggest factor. So.
Okay. And do you consider agarose-based media compressible or incompressible?
Well, agarose-based media is definitely compressible.
And do you need anything to do anything differently when packing incompressible resins in stainless steel columns?
So that's a great question, and the answer is yes. Since you can't see the top of the bed, you don't know when you're getting near it necessarily, you don't know when you're getting near it by eye. So the thing to do, and this is what we actually did when I packed at the 1.8 meter scale with CHT, is figure out how tall the bed is based upon how much you put in, and once all the bed is consolidated, which just means giving it a few minutes really to get bottom at a reasonable flow rate, you start lowering the top flow adapter and you bring it down to maybe 2 centimeters above where you think the top of the bed is, and you can check HETP and asymmetry at that point. And if it passes, you're done. Maybe the bed's a little taller than you thought it was going to be. If not, lower the head by a half centimeter or so and retest, and you keep doing that until you get within range, and that actually worked very well for us at the 1.8 meter scale. So, and if anybody wants more information, contact me directly. I'd be happy to go over it in more detail.
So. Okay. How do you set HETPA's requirements with process development data?
So during process development itself, typically you don't. At small scale, you pack a column, you pretty much get what you get, and you just make a note of that so that you know what ranges you've used as you scale up. If you are doing step elution, frankly, neither of these really matter very much. You need one plate per meter, as I think I alluded to in the talk. And asymmetry is more a function of how big an elution volume you actually want to get. So if you're doing a gradient elution, of course, then plates per meter matter to some extent. But I've never seen anyone, frankly, do a study that says, well, it turns out that we tried 2,000 plates per meter and that wasn't enough. We tried 3,000 and that wasn't enough. But we went to 3,500, that was enough, and so that's our lower limit. So pretty much just keep a record of what you use in process development and try to be as generous as possible on the manufacturing floor, because the people on the floor have a lot to do, and the wider the ranges, the happier they are.
Okay. And do you recommend performance repeat efficiency testing if the adapter is lowered to reduce headspace?
Oh, after it's packed originally, yeah, that's not a bad idea, because you're going to want to know where you are at that point, just to keep everybody happy.
Okay. I think we have time for just one more question. If we didn't get to your question, you can go ahead and continue to enter them, and Mark can follow up with you directly. So the last question is: you mentioned an artificial second peak when using sodium chloride as a test solute.
Yeah.
Would such an artificial peak appear while using sodium chloride gradient?
No, so that peak is just during the HETP test itself. During actual processing of the column, you will not see that.
Okay, great. Thanks, Mark.
Sure, anytime.
And thanks to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.